Hello, we are talking about column efficiency in column chromatography and the resolution. So, chromatography columns are considered to consist of a number of adjacent zones, as we have discussed in the previous lecture, and they are referred to as the theoretical plates. Now, these adjacent zones, in which there is a sufficient space for an analyte to completely equilibrate between the two phases, the stationary phase and the mobile phase. And each such zone is called a theoretical plate and denoted by letter N. The length of column when you talk about it contains one theoretical plate is referred to as the plate height, right? That is denoted by letter H. So which has units of length normally in micrometers. So numerical value of both N and H for a particular column is expressed by reference to a particular analyte, because each analyte is going to behave differently in a given stationary phase and in a given mobile phase. So plate height, when you talk about, it is simply related to the width of any analyte peak and the distance it traveled within the column, that is given by x. So when you talk about the behavior of a column consisting of number of theoretical plates, within each of zones you have perfect equilibrium between the two phases. Of course it is not 100%, but maximum perfect equilibrium can be achieved, and it shows that the continuous or packed type of columns would could be divided up to a number of layers, each of which has a weight equivalent to theoretical plate, and the height of such a layer is called HETP, or height equivalent to one theoretical plate. Now, why the word distillation has come? Because the theoretical plate concept itself has originated from or with reference to the distillation process and the distillation column. So the word is utilized as distillation column. However, it is similarly applicable to column chromatography. So when you talk about the theoretical plates, the height, when you talk about the height of a theoretical plate, it can be calculated when both n of the column and L of the column, they are known. So L is the total length of the column and N is the number of theoretical plates. So that will give you the value, that is HETP, which is nothing but height of each of these theoretical plates. Right? So of course, efficiency of the chromatography column is optimized when is n maximized. So more the length of the column, more are the theoretical plates, better is the efficiency. But when to have number of theoretical plates more, that time it is very sure that in a given length of the column, if you want to increase the number of theoretical plates, then it is very important to have the size of each theoretical plate should be minimized, right? So to get maximum n, HETP should be minimized. So, in this context, the equation, that is another way that expresses the efficiency of the column chromatography, is known as the Van Demeter equation. It considers the three factors along with the mobile phase linear velocity, which will affect the efficiency, and therefore HETP values are going to get affected. So these factors are represented by variables a, b, and c in the Van Demeter equation. And the equation goes as HETP equal to a plus b upon mu plus c into mu. Now, the size of uh, or height of each theoretical plate ultimately is governed by the size of the support matrix porous material that is used. So the diameter of that material is going to decide the flow of the liquid, the velocity of the mobile phase, and then equilibration of the two of the analyte in the two phases. All right. So whenever we talk about the separation of the two components of a sample, in chromatography, the it is function of retention times. So when we say retention time, that is the time that analyte takes while traveling down the column. So that is the time with the stationary phase, and the time when it gets eluted, that is TR. So this ratio, separation of two components when you are talking of a sample, is function of ratio of the retention times. So this ratio is known as separation factor. So the separation factor is another important thing that needs to be understood properly. The separation factor, when you talk, is a function of the stationary phase and can be varied in order to improve the resolution by varying the stationary phase, because the particle size, as I said, right, the porosity of the gel matrix, all these things are going to decide the flow rate, the mobility of analyte, and ultimately the efficiency and resolution of the chromatography system. So to improve the efficiency, you can improve the quality, or you can say the resolution of the chromatography column by changing the stationary phase, so that the separation factor is good and you can get proper separation of the two analytes. So when it comes to the resolution, uh, and that needs to be improved, it can be how can we improve the resolution? So as we have seen, the number of theoretical plates are going to be important in increasing the resolution phase, uh, sorry, in increasing the resolution of the chromatography system. So if you see in the diagram given next to this, you can see the relative distribution on the column, and the volumes are specified on X. It is the a relative solute concentration is there on the y-axis, and you can see three different types of peaks. One is a very sharp symmetric peak, right? Another one is very much spreaded from this end to that end, and the third is in between the two. So why this kind of variation can be achieved using the same chromatography column and the same analyte separation? Now this can be very well understood that the n factor, the theoretical number of theoretical plates, are different in each of these cases. N equal to 10, it is very widely spreaded, a flat peak is seen. If you increase the number of theoretical plates 10 times, that is n equal to 100, you get a better peak, but again it is wide and diffuse peak. But if the number of theoretical plates are raised to 1000, then you can get a very sharp and fine symmetric peak, right? So in chromatographic separation, the ideal Gaussian shaped peaks are not really obtained, but you may get some asymmetric peaks also. So, whenever there is a gradual rise or a sharp fall in the peak, you call it as a symmetric peak, and it is fronting, right? So, in addition to such diffuse peaks, you may get skewed peaks, and those which are having the sharp rise but the fall is extended, and that is called as fronting phenomena. So this kind of variations you will get, and this can be caused due to various factors, including the theoretical plate is one phenomena that contributes, but loading of the column, the flow rate of the mobile phase, and the amount of the sample that is loaded in the column also are going to cause diffusion, and that is going to lead to the diffused peaks, or diffused in a asymmetric way, and leading to fronting like phenomena, right? So very important is key, you have to improve the number of theoretical plates, and that can be done by managing the stationary phase, by changing or varying the stationary phase. So in practice, when you're talking about varying the stationary phase, the number of theoretical plates that gives a good successful resolution is to be achieved. So as you can see in this diagram, on left hand side, you can see four graphs, four chromatographs A, B, C, and D. As you can see, the first graph, that is graph A, is showing us the resolution of the two peaks is really poor. The poor separation factor. So what it indicates, there are overlapping peaks and separation is not good. As in case of B, you have better separation, but yet it is not complete separation till you have some connection between the two, right? The third is case C, where again it is not really very good separation, right? Because you can see the shape of each of the peak. It is not very balanced Gaussian normal distribution curve, and again they are like still they are connected with each other. Whereas the last one, the D1, shows good separation factor. So in this case, what is the factor that leads to such variations? So surely the factor that can be improved is the number of theoretical plates. So if I increase the number of theoretical plates, this poor resolution can be changed to a better resolution, as in case B. So case E was poor. By increasing theoretical plates, I can get better resolution, as it is seen in B. But here, poor separation factor is another component. So in spite of having large number of theoretical plates, separation factor is poor, and so the resolution is not really good. So this separation factor is one of the important thing that needs to be taken care of, right? Now going back to the resolution and the separation factors, here is one good example which is cited from fire debris analysis. The goal is to avoid co-illusion, right? When we say good resolution, that means they are totally separated. They are not getting co-illuted. So what you ultimately aim is at avoiding the co-illusion. So in this case, you can see the coeluting fractions, but if you note properly, the height at which they are connected to each other, or there is a connect between the two peaks, right? Their join is going to vary as compared to the baseline. And the sharpness of the two connecting points, if you observe in case of figure 2 and 3, also is going to vary. So how it can be taken care of. So when we are talking about a separation of any compound, the compound's contribution to overall structural information provided by mass spectrophotometer will not be distinguishable. But their identification in this case will get hampered if you get such overlapping peaks, right? Now, this happens when you are going to have baseline resolution is the factor that needs to be taken care of when you are talking about separation of the two peaks. So baseline resolution is the ultimate goal for all the peaks, right? So in the fire debris analysis, this goal can never be achieved in practice. That can be a case in very many complex samples which we obtain from biological sources also, because there are many molecules which are very much similar and are just varying by addition of a simple functional group or a metal ion attached to it, and then complete baseline separation or resolution may be a challenge. So here in this case, if you see, the resolution factor is going to be important. If the resolution factor is below 1.5, then it will not provide you complete separation. And if the resolution factor is more than 1.5, also has no much of an advantage. So resolution factor of 1.5 was found to be better for resolving the peaks which are generated from fire debris analysis, as an example. So the peak configuration, right, is very important, and we need to take care that how one can get a good separation and there is no co-illusion of the analytes. Now, these are the parameters that we have seen how to describe a chromatogram. This is the detention time of the analyte in the stationary phase. This is the baseline. This is the peak. This is the width of the peak. This is height of the peak, and this is the height of the peak, and this is the half width or width at half height. That is why it is referred to as WH. So WB is baseline width. WH is width at half line of the peak. So this is how we talk about a general chromatogram to describe the parameters. Now let's look into the factors which can affect this good separation. So first factor is the n, that is the theoretical plate. So how do n relate to peak width? So it is peak width is proportional to square root of the number of theoretical plates. What is that? Peak width, just now WB that we have seen is proportional to the square root of number of theoretical plates. So surely better the theoretical plates, good is going to be the width is going to get reduced, and you are going to have a sharp and well balanced peak. Now, how do n relate to column dimensions? So efficiency of column is function of its dimensions, because the flow rate and the compound and its retention is going to be affected by the number of theoretical plates. So diameter to length ratio of the column also is going to be very important. Uh, when you talk about the column efficiency, the number of theoretical plates per meter area of the column is often used to compare the columns. So again, it is the theoretical plate is going to be depend upon what is the nature of the stationary phase and how does the analyte interact with it. Every analyte is going to interact differently, and so the theoretical plate height for each type of analyte and the total number of theoretical plates are going to be different. So height of a theoretical plate is also known as the height equivalent to theoretical plate. It is also a good factor to be monitored, because it is a measure of zone broadening. So lower the HETP values, narrower are going to be the solute peaks. Lower the value of height of the theoretical plate. Just now in the previous case we have seen this is the height of the theoretical plate. Sorry, not in this case, I'm sorry. In this case, this is the height of the theoretical plate, right? Single each individual. So smaller the height of the theoretical plate, better is going to be the peak. That means narrow solute peak, narrower peaks you are going to get. When we talk about column chromatography, number of segments that theoretical plates with having height that is equal to h, here is going to be defined by the size of the or diameter of the resin particles that are chosen. So within each segment, equilibrium is supposed to exist. But what is the size of that resin, and how well it is going to allow the flow of analyte, and how strongly it is going to absorb the analyte, all these things are going to decide the ultimate movement of the analyte through the column. So, as the adsorption operations, equilibrium is not often achieved in chromatography, so that the theoretical plate concept does not accurately reflect conditions in the column. It is one of the majors, right? But the idea of theoretical plate is applied extensively because it provides a parameter, that is the plate height, which can be used to characterize zone of spreading. So it is a theoretical concept, that is theoretical plate. So as exactly you are not going to see such segments, but that tells you or gives you an idea about the area and the height of that particular zone where the distribution of an analyte would take over, right? The characteristic zone of spreading of an analyte. So use of plate height, which is also known as height plate equivalent to a theoretical plate, is to be considered. So it is theoretical plate is important, but more important is height of each of the theoretical plate, and which is ultimately going to be governed by the diameter of the pores and the diameter of the resin particles. Now this is what the formula we had written, which says n, that is number of theoretical plates, is equal to 16 into VE upon W. VE is with respect to when you are talking in terms of elution volume, right? So n is the number of theoretical plates. V is the distance on the chromatogram, which is corresponding to the elution volume of the solute, and W is the baseline width. Baseline width, we have seen this baseline width, right? So uh, the peak, when you are talking about the line drawn tangent to the inflation point of the curve, right? So uh, if the sample is introduced in the column as a narrow pulse, you are going to get a better resolution. So number of theoretical plates is related to HETP, that is what we said. So what is the relation between N and H and L? L is the length of the column, H is the height of the theoretical plate, and N is the total number of theoretical plates, right? So N is equal to L upon H. So value of H and N are going to vary for a particular column depending on the component being separated. So though the length of the column is same, but the number of theoretical plates, that is the area or the zone where the distribution of an analyte between stationary and mobile phase is going to occur, is going to be determined by the partition coefficient for that analyte for the given stationary and mobile phase, right? Distribution coefficient is going to be important factor in this, and that will be ultimately governed by the molecular nature of the functional groups attached to that analyte and its absorption on the stationary phase and its interaction with the mobile phase. So the number of theoretical plates and height of each theoretical plate is going to be dependent on the component. It is not dependent on the column alone or column length alone. It is going to be dependent on how that analyte interacts and gets equilibrated between the two phases. So this is the formula that talks about N upon L is equal to, that means H, right? N upon L equal to 5.54. Now what is the difference in the numbers? In place of 16 you have 5.54, and VE upon W whole square, that was the previous formula that you have seen, right? VE upon W whole square, and here is 16. In place of 16, 5.54 is used, wherein you are talking about half the width of the column of the peak. I'm sorry, uh, the width at half the height of the peak. That means the inflation point. For example, I go back to this diagram. This is the baseline, that is WB, and this is the inflation point where the width of the column is width of the peak is measured, and it is given as WH. So in place of WB, if you are using WH in the formula, the number changes as 5.54, because we have seen in the previous discussion that is in the formula it is all about the 4 sigma, which is the factor that is taken into consideration when we are calculating the baseline of the peak, right? So at the half of it, it is 2 sigma, and so the factor 16 gets converted to 5.54 when you are deriving the formula. Right. So the parameter which is closely related to theoretical plate that we are discussing is the height of the theoretical plate, or height equivalent of the theoretical plate, right? So height equivalent of theoretical plate is nothing but column length upon N, and it indicates column performance which is independent of column length, because as I said earlier also, the height of each of these equivalent height equivalent of the theoretical plate, HETP or H, is going to depend on how that analyte interacts with stationary phase and mobile phase. Now the factors that impose a strong effect on the number of theoretical plates: the size of the particle, right? The diameter of the resin particle that we are talking about is going to be very important factor. The interconnecting tubings, dead volume, very strong impact it is going to have on the elution time, and then it is going to affect the performance. The profile of the gradient that you prepare of the elution buffer, that is going to be responsible for the rate of elution and the peaks that will appear as the elution takes place. So ultimately the gradient buffer that you prepare is going to be very crucial factor and is going to have a strong impact on chromatogram and the analysis based on that. So temperature of the column is another important factor in addition to length of the column, composition of stationary phase, composition of mobile phase, and shape of the particle. Because all these things are going to govern how an analyte is going to interact with stationary phase, interact with mobile phase, and how it is going to get equilibrated between the two phases. More the interaction with stationary phase, longer it will remain in the stationary phase, and t prime r will be more. If it is going to interact more with the mobile phase, then it will elute fast. So these are the factors which are going to decide the number of theoretical plates and then the efficiency of the column. Let's take an example of height equivalent of a theoretical plate. So if I have a well packed column and the plate height is say roughly to be 2.5 dp, this is distribution coefficient we are taking into consideration, right? So when when you are having a column packed with 5 micron particle size, for example, and the plate height that has been found to be 12.5 for a given analyte, 12.5 micron, right? So a typical 15 centimeter long column packed with 5 micron material will give you n equal to l upon h. So that comes about 1,50,000 plates. But if you have 12.5 micron size, or a typical 5 centimeter long column packed with 5 micron material should have n equal to L by h equal to 1,50,000 micron, right? And this is divided by 12.5, that is the plate height. So you are going to have 12,000 plates in that 15 centimeter column. But if you talk about the same column about 15 centimeter long, but it is packed with material whose diameter is about 3 micron. Now again, though the length of the column is same, the number of theoretical plates and the height of each plate is going to change, and by changing this from 5 micron particle to 3 micron particle is going to increase the number of theoretical plates from 1,50,000, it is changed to 20,000. So it is entirely changed, and the efficiency of the packed column would be will get altered by changing the particle size, right? Of course, flow rate is another factor which is going to be important, that is going to decide the efficiency of the column and number of theoretical plates, and the height of each plate and everything. How? Let's talk about it. When I talk about the temperature factor, how it is going to be affecting the theoretical plates, right? So effect of temperature on analyte retention and selectivity is known. It is going to be different for each analyte and will depend on the property of mobile phase and stationary phase. So generally, if you increase the column temperature, uh, the viscosity of the mobile phase is going to get reduced, right? At the same time, the interaction between the analyte and the stationary phase also is going to get affected, because decreasing the when you increase the temperature, the retention time of polar compounds uh, will be decreased, and that of non-polar compounds have longer retention times. So polar compounds will get eluted faster and non-polar compounds will be retained longer if you increase the temperature. So because temperature is going to decide the distribution coefficient of the analyte between the two phases, that is mobile phase and the stationary phase, and it is going to affect the selectivity of the separation. Here another example is given, that is of reverse phase chromatography. Decreasing temperature increases retention of polar analyte relative to non-polar analyte, exactly opposite, because we are talking here in case of reverse phase chromatography. Overall, to say कि temperature has effect on distribution of an analyte between the two phases, and ultimately its equilibration in a given zone, and ultimately the number of theoretical plates and height of each plate is going to be different. So if temperature is not tightly regulated or controlled, then it can lead to variation in retention times for the same analyte. Peak shape also will be changing, peak areas also will be different. So the reproducibility of the entire process will be affected, right? And the same system, same analyte, same mobile phase, but if you change the temperature every time, with change in the temperature you will get a different kind of chromatogram. So inconsistency will be there if it is uh, if the factor, that is temperature, is not controlled. So in addition to the diameter of the particles, in addition to the flow rate, in addition to the nature of the resin, temperature is one of the important factors that decide the efficiency of separation of analytes using column chromatography. Also important is the time required for separation is very important, and again it is governed by temperature, the diameter of particles, interaction of analyte with the stationary and mobile phase, and so on. So to increase the uh, speed of the process and to reduce the time required, maybe we can increase the flow rate by changing the temperature, by managing the pore size of the resin particles, right? But if and by increasing the length of the column also, you can facilitate the number of theoretical plate, and more the theoretical plates, better is the separation. That is what, but longer the column, more the time will be required. So in such cases, the things that help to improve the efficiency can affect the speed of the process. So in such case, you may proceed to increase the pressure under which the column would work and lead to fast or speedy elution of the analytes. But for such purposes, the stationary phases are to be compatible for the pressure applied. And that is where we talk about HPLC, which will be the part of next topic, next discussion, next lecture.